let me remind you that the last time we discussed the energy spectrum of the linear rigid rotor, and we constructed an orthonormal set of vectors called Jm, are composed of eigenvectors of our Hamiltonian. This set of vectors is labeled by the quantum number j, which can take integer or half integer values, 0, 1 half, 1, 3 halves, and so on and so on. Half integers mean odd number divided by 2, right? And for a fixed j, the number m can run through the set minus j in step of 1 to j. And each ket vector of this family by construction is an eigenvector of the operator j squared with the eigenvalue j times j plus 1 jm. And of course all of them are eigenvectors of the operator j3 with eigenvalue m times eigenvalue m, right? Okay, and it remains to find out, to work out explicit formulas for the action of the other two operators, j plus and j minus, on these vectors. So these vectors are assumed to be orthonormal. So Jm, Jm with j prime m prime is equal to delta jj prime delta m prime. They form also Gounod set of vectors because they belong to different eigenvalues of Hermitian operator. And upon normalization, we get an orthonormal set of vectors. And by construction, the application of the latter operators, j plus or j minus, gives us a nearby vector of this family that is something proportional to jm plus minus 1 with some proportionality coefficient jm plus minus 1. And our problem is to identify this complex number Cjm. And to do this, let us compute the norm of the vector on the right. This is given by the following. It is given by the expectation value of the following operator. Keep in mind that j plus and j minus are adjoint to each other, that is, Hermitian conjugation of j minus gives us j plus, and vice versa. We get immediately that j minus plus times j plus minus jm. So this is a norm squared of this ket vector. On the other hand, we can use the definition of the operator j squared in terms of the operators j plus, in terms of the latter operators and j3. Let me remind you that for j squared, we had the following expression: j j minus plus, j plus minus, minus plus j3, J3 plus minus J3 squared J3, and that's it. Okay, and using this definition, we can rewrite this operator in between in terms of the operator J squared and J3. So we can proceed as follows: Jm J squared minus J3 squared minus plus J3 Jm. Now applying the operator J2 and J3 on the ket vector Jm, it is eigenvector according to the definition, we get immediately that this is given by the eigenvector J squared, that is J. Let me proceed below. That is J plus 1 minus m squared minus plus m. Okay. And with the help of little algebra, we can rewrite this expression in this way. We can factorize it into the product of two numbers, j minus plus minus m times j plus minus m plus 1. And as I seen, this number is always positive when m runs in between minus j to j. Neither bracket vanishes. But on the other hand, this number is equal to c j m plus 1 modulo squared, because we suppose that all the vector jm have norm 1. So j norm 1. So we know the absolute value of the complex number c. So in terms of in earlier forms, we can write this complex number c m plus minus 1 as square root of j minus plus m times j plus minus m plus 1 times some phase factor f and j. F and j is an arbitrary real number. Okay, using this c, we can rewrite the formula for the action of the ladder operator in this way: j plus minus on jm is equal to square root of j minus plus m, j plus minus m plus 1 times jm plus minus 1 times this phase factor, unknown phase factor. Do you agree? What about this factor, this phase factor? Actually, we needn't worry about it because of the ambiguity in the defining of the basis vectors Gn. Yes, this normalization condition doesn't specify these vectors completely. There is an infinite phase ambiguity, so I can include this phase factor in the definition of my vectors, of my basis vectors. So I can absorb this phase factor in the definition of the basis vector. And from now on I may assume that the basis vector was chosen in such a way that the operator j plus j minus act on this basis vector, multiplying them by some real number, real positive number. So in this special basis, the expression for the action of the ladder operator simplifies, and we are left with this formula. We get this formula. So taking together these formulas for J3 and J plus minus specify the action of the operators J and hence angular momentum components on the basis vector Jm, And all these vectors are eigenvectors to J squared, that is, they are eigenvectors of our Hamiltonian. Okay, but we are by no means finished with this story. What we have found, we have found our admissible values for the energy operator. Admissible value, eigenvalues of energy operator should be proportional to G times G plus 1, where G may take only integer or half integer values. And we still need to decide which of these eigenvalues do occur in the energy spectrum of the rigid linear oscillator, rigid rotor. And in order to answer this last question, it is convenient to pass in the coordinate representation. In the coordinate representation, we have started with the components of the angular momentum given by the first order differential operator of this form. Epsilon ijk xj d by dxk, where x are Cartesian coordinates in free space, epsilon is a Levi-Civita symbol, and as usual we assume summation by repeated indices jj, kk. And these first order differential operators M are supposed to act in the space of complex valued wave function psi of x1, x2, x3. But we should keep in mind the constraints on the radius vector, because our particle, our mass, is confined on the surface of sphere. That's why the magnitude of its radius vector is fixed. It is given by the constant r squared. And in order to account for these constraint, it is convenient to pass to the spherical polar coordinates. Let me recall that. The standard formulas for this transition. The polar, so we are passing from x1, x2, x3 to the spherical polar coordinates rho, theta, and phi, where rho is the magnitude of the radius vector x, x1, x2, x3. Theta is a polar angle, theta, and phi is the azimuthal angle. And these coordinate systems are related to each other by the standard formulas. Let me remind them to you. X1 is given by rho sine theta cosine phi. Accordingly, x2 is given by rho sine theta sine phi, and x3 is given by rho times cosine theta. So think the radius vector rho is now constant. It is fixed by r. Our wave functions are actually functions depending on their angle variables. Functions of theta and phi. And the inner product in the space of complex valued functions of theta and phi, this is just complex valued functions on two spheres. You can think of them as complex valued functions on two spheres, parameterized by the angles theta and phi. And the inner product in the space of such a complex valued function is given by the integral of a sphere. Phi 1 star phi theta, phi 2 phi theta, and sine theta d theta d phi. Sine theta d theta d phi is just a standard area element on the sphere. Standard area element on the sphere. And by definition, the angle theta varies 0 pi, and pi runs 0 to pi. Okay, is it clear? No. With a bit complicated computation, it is also possible to write down expressions for the angle momentum operators in terms of spherical coordinates. To be sure, you have encountered these expressions in your course on mathematical physics. As to me, I have never been able to get them by heart, so I will just copy them from my notes. Let me erase something to make more space. So, in terms of spherical coordinates, the component of the angular momentum operator take this form: minus IH bar sine phi d by d theta plus cotangent theta sine phi d by d phi. M2 is given by IH bar cosine phi d by d theta plus tangent theta d by d phi. And of course for M3 we have IH bar d by d phi. And combining these operators M1 and M2, we can write expressions for the latter operator J plus minus. Recall that they are given by these linear combinations, and our J3 is given by minus h bar to the minus 1, M3 is proportional to M3. So for J plus minus, we'll get exponential function of plus minus I phi plus minus d by d theta plus I cotangent theta d by d phi, and J3 is just minus I d by d phi. Okay, and from now on I will change my notation. Instead of quantum number J, which labels the set of my eigenvectors, I will use the number L. The reason for this change will be clear below. So now my basis vectors are labeled by two numbers, L and M. So M runs from minus L in steps of 1 up to L. And in the coordinate representation, we present these eigenvectors by the eigen functions, and I will denote these eigen functions by y capital, y ln of theta and phi, theta phi lm. Let us consider the highest vector in this sequence, that is vector with maximal projection of J3, maximal eigenvalue of J3. That is the function YLL. By definition, this highest vector or highest wave function is annihilated by raising operator J plus. By definition, this function is annihilated by a raising operator, and of course it is an eigenfunction for the operator J3, for the operator J3 with eigenvalue, with value of projection L. Explicitly, these two equations have this form. So we substitute operator J plus and J2. In coordinate representation, we get two equations. The first one, d YLL by d theta plus I tangent theta while LL by d phi is equal to 0. This equation and that equation is given by d while LL by d phi L while LL. So we have two differential equations, linear differential equations on our function while LL on the highest value of J3. Okay, which of these two equations looks simpler? This or that? What do you see? Which is simpler? I suppose the right one. So let us start to solve this system from the right equation. This equation can be easily solved by separation of variables. So this is linear first order differential equation, and we can always solve it by separating variables. The answer is almost obvious. So while LL of theta phi is given by exponential of IL phi for some unknown yet unknown function FLL. Just integration constant for this equation. And now look at this equation. This is a very remarkable equation actually. And by definition, our Eigen functions, why? They are functions, complex valued functions on sphere. So they might be periodic in phi with period 2 pi. So y LL theta phi plus 2 pi should be equal to LL theta phi. Just in order for this eigenfunction to be single value, that is, function in the string mathematical sense. But if you translate here phi to pi, we get times IL to pi. So in order for these two expressions to be equal to each other, this factor to pi, this exponential factor should actually be equal to 1. So and this in turn only possible when the number L is integer. So L is integer. Otherwise, our wave functions are not single valued. They are not functions or complex valued functions on sphere. So in particular, half integer values for L is forbidden. Half integer values are forbidden. That's the reason for the change of the variables. The original index j might take all the values, integer or half integer, but when it comes to rigid rotor, we see that for angular momentum, of the rigid rotor, this L may take only integer values. Okay. This is an important point. Now we can substitute this equation, this expression for y into the first equation to get a differential equation for the factor f, for the function f of theta. Let me write it. So upon substituting this function y in this form into this equation, I get the following differential equation for f L df by d theta minus L cotangent theta f L is equal to 0. Again, it is not hard to solve this equation by separation of variables, and the answer reads f L theta is given by some integration constant c times sine to the L of theta. So, and overall we have the following answer for the function YLL. Some constant theta as c times sine to the L exponential function, exponential of I L phi. Okay, these are integration constant c can be fixed by normalization condition, by the normalization condition. And so this is the wave function for the state with the maximal possible value of J3, with the maximal possible projection of the dot component of the angular momentum to the axis. And the other wave functions in this sequence can now be obtained by repeated application of the lowering operator J minus. So applying the operator J minus to these functions, we get the following recurrent relations. Recurrent relations. So with all normalization factors, we get that while L m minus 1, that is previous function, in the sequence given by 1 over square root L plus m, L minus m plus 1, e to the minus I phi L times minus d by d theta plus I tangent theta d phi y L m. So starting with the highest wave function YLL and applying successfully this lowering operator, we can reconstruct all the other wave functions in the sequence. Actually, these wave functions YLM are well known. They are nothing but known as, they are nothing but the spherical functions. They are known as spherical functions. Or more common name, spherical harmonics. Spherical harmonics. Spherical harmonics. Spherical harmonics. In particular, the function while Lm is called the spherical harmonic of degree L and order m. The spherical harmonic of degree m and order m. It is also possible to express these spherical harmonics in terms of the so-called associated Legendre polynomials. Associated Legendre polynomials, P, M, L, X. Associated Legendre polynomials. Namely, we can write while Lm of theta phi as 1 over square root of 2 pi e to the minus e to the Im phi times Legendre polynomial R of cosine theta. So the angle theta enters these expressions through the cosine in polynomial way. In polynomial way. I will not present here explicit expressions for the Legendre polynomials. With all normalization factors, they are a pretty mess. You may find them in many textbooks. Instead, I would like to draw your attention to the well-known mathematical fact that the spherical harmonics form a basis in the space, in the Hilbert space of functions on sphere. So any continuous function on sphere, any continuous function on sphere can be expanded into a series over the spherical harmonics. So we can write sine of theta phi as double sum L from 0 to infinity, m from minus L to L, CLM, while LM theta phi. On the other hand, we know that the square integrable functions on sphere, they constitute the Hilbert space of states of our rigid rotor, because originally our rigid rotor is just a point mass moving on sphere. So in coordinate representation, it's space here with space of states. It's just the space of square integrable functions on sphere. And any such function can be expanded into the series over the spherical harmonic. So this proves that this basis of eigenstates, eigenfunctions for the Hamiltonian of the rigid rotor is indeed a basis, is indeed a complete set of eigenvectors. And we conclude also that the possible this energy spectrum of the linear rigid rotor is given by these numbers: h bar squared over 2m r squared, L plus 1, where L may take all integer values, natural values, 0, 1, 2, and so on. So we see that each eigenvalue, that the L's eigenvalue is degenerate, and with multiplicity to L plus 1, with multiplicity to L plus 1, it is degenerate with respect to the quantum number m, because m may run from minus L to L. Only the ground state, that is state with the minimal possible value, which corresponds to L equals 0, is non-degenerate. Only the ground state is non-degenerate, all the other states are degenerate. Perhaps it makes sense to draw some diagram to help you to memorize the structure of the energy spectrum. Let us draw the following diagram. The horizontal axis for the possible values of m, the vertical axis for L, and now one, two, three, four. Now let me draw the right angle which opens upward, and inside this angle area I mark the points with integer coordinates. These integer coordinates. All these are points inside, integer points inside the corner, corner area. They correspond to the eigenstate of the rigid rotor. So for a given number L, we have 2L plus 1 states belonging to the corresponding value of energy, that is E L, which is equal to L plus 1. And the origin corresponds to the ground state. And to the ground state. By construction, this number m labels the possible eigenvalues of projection, of the third projection of the angular momentum, projection on the third axis. So if you write these are this circle, and so we see that here J3, which is proportional to N3, so these points correspond to the possible values for the third projection of the angular momentum. So we see, for example, if L is equal to 3, we have 1, 2, 3, 4, 5, 6, 7 possible values for the projection. So it may be 0, 1, 2, or just 3. -1, -2, and 3. So this depicts all possible values for projection. Questions, please? Okay, if no questions, let us take a break, 5 minutes. Okay, let us continue our lecture and pass on to the next topic, which is called Schrodinger and von Neumann equations. Schrodinger and von Neumann equations. Schrodinger and von Neumann equations. Everything we have discussed so far could be called quantum statics, that is, states and physical observables at a given instant of time. Now I'm going to discuss dynamics, that is, how physical states and quantities evolve in time. And let me remind you that in the classical mechanics, a mixed state is usually defined by the so-called probability distribution rho, which is supposed to be positive semi-definite function on the phase space of Q's and P's, subject to the normalization condition. The integral over the phase space of rho is equal to 1. So rho is rho bar B dt distribution. And the dynamics of mixed states are governed by the so-called Liouville equation. Liouville equation, which is basically a first-order differential equation in time of this form. So h of Q and P is a Hamiltonian of the system, in the Hamiltonian of the system. And as we established at the previous lectures, the right quantum mechanical counterpart of the probability distribution in quantum mechanics is given by statistical operator. In quantum mechanics, we describe mixed states by statistical operators or density operators. Statistical operator. And this operator is also assumed to be positive semi-definite, that is, and is normalized with respect to the trace. So the trace of the operator rho hat is equal to 1. Now, with the correspondence principle in mind, it is not hard to guess what might be, how to translate this Liouville equation into the quantum mechanical context. Do you see? What might be the analog of the Liouville equation in quantum mechanics? Please share with us your ideas or hypotheses. Don't hesitate. No idea. Yes, and what about Poisson bracket? The Liouville equation contains physical quantities like Hamiltonian. It also involves density operator or probability distribution, and the Poisson bracket of rho and h. What should we do with this Poisson bracket? Yes, you're right. So, passing to the quantum mechanical description, we just replace rho and h with corresponding Hermitian operators, and so doing the classical Poisson brackets are replaced by the quantum Poisson brackets invented by Dirac, which basically is a commutator of the two operators. So I can write the following equation R, which is and this equation is known as a von Neumann equation. Von Neumann equation, or quantum Liouville equation if you wish. And this von Neumann equation, similar to its classical counterpart, expresses causality in quantum mechanics. So, given some state rho naught at some initial time moment t naught, then we can solve this equation for rho to identify all the future states our system will get through in the course of its evolution, as well as all the previous states our system went through to get to this state rho 0. Okay, so everything looks quite natural, but before we eventually adopt this von Neumann equation as the basic dynamical equation of quantum theory, we need to check that its solutions satisfy all required properties of statistical operators. And what are these properties? Do you remember? Operator rho should be Hermitian, it should be positive semi-definite, and satisfy the normalization condition. Okay, let us start with Hermitians. So Hermitians. So we need to check that the operator rho is Hermitian for all times. We know the initial operator rho naught is Hermitian. and to prove this, let me introduce the following operator R as the difference of rho and rho dagger. This operator R measures the deviation of the operator rho from being Hermitian, right? Now differentiating this operator R with respect to time and using, which gives me d rho by dt minus d rho dagger by dt, and using the von Neumann equation up here, I can rewrite this as a commutator through the commutator with h. Here I use the fact that the operator H is Hermitian. So finally I get that dr by dt is equal to 1 over I h bar R commutator with H. So I see that my operator R satisfies this linear differential equation subject to the initial condition, that is R at T naught is equal by rho naught minus rho naught dagger, that is equal to 0. Now, by the unique existence theorem for the systems of ordinary differential equations, I conclude immediately that the only solution, the only function R satisfying both the differential equation and the initial condition is that R of t is equal to 0. So the operator rho is Hermitian for all times. Is it clear? Do you follow me? Yes. Yeah. The initial operator is Hermitian, right? But then we need to prove that the evolution of this operator is also Hermitian, so that Hermitian operator rho naught evolved to Hermitian operator, because statistical operator should be Hermitian at any time moment. But it follows, as we see, it follows immediately from the structure of the von Neumann equation. If we start with the Hermitian operator rho naught there, we can get only Hermitian operator at the later previous times. Okay. The next thing to check is normalization condition. Normalization. Again, we assume that the initial state rho naught obeys the normalization condition, that is trace of rho naught is equal to 0. And we can try to prove that the solution for Neumann equation, this initial data, also satisfies this normalization condition. So let us write the trace of rho t. So trace is a linear functional on the space of operators. So applying the operator of partial derivative with respect to t, I can change, transpose trace and the derivative operator, and to write this as d rho by dt. Now again, using the von Neumann equation up here, I can replace this partial derivative by the commutator with the Hamiltonian. And we know that the trace of the commutator is always zero because of cyclicity, the trace cyclicity property. The trace of the commutator of two operators is always zero. So this means that the trace of the statistical operator doesn't vary with time. So trace of rho of t is equal to trace of rho naught, which is equal to 1. And this gives us the normalization condition for all times. Questions? Because r equals 0 is a solution, is a unique solution to our differential equation plus initial condition. Is it clear that zero function r satisfies this equation? This equation. 0, 0, 0 on the left, 0 on the right. Right? And it also satisfies the initial condition. Now we apply the unique existence theorem for the solutions of differential equations. So this is the general solution to our equation subject to the boundary condition. So if we are able to satisfy our equation with some function, then it is a solution. And we see that zero solution is solution. And this means that the only solution to this equation plus boundary condition is 0, r. So it is 0 as a solution to the differential equation. And we obtain this equation by identical transformations using the von Neumann equation. Okay, the verification of positive semi-definiteness of the statistical operator is a bit more tricky, and I will postpone it to the very end of this section. We will return to this question later. At the time being, let me know that if the initial state rho naught, rho pure, is pure, then so are all the subsequent states resulting from the von Neumann equation. So pure states evolve to pure states. And to prove this fact, we can use our favorite test for purity. Do you remember how to decide whether if this edge is pure or not? What is our favorite purity test? P-test. No idea. Who is psi? Who is psi? Yeah, that's right. So rho squared should be equal to rho. So statistical operator rho describes a pure state if and only if its square is equal to it. If it coincides with its square. Okay, and this motivates us to introduce the operator C, given by the difference rho squared minus rho. So this time this operator measures the deviation of the operator rho to describe a pure state. And using this trick, let us compute the time derivative of this operator C using the von Neumann equation. We get dc by dt is given by the Leibniz rule. I get d rho by dt times rho plus rho times d rho by dt minus d rho by dt. And now using the von Neumann equation up here, we can proceed as follows. This is given by 1 over I h bar h commutator is rho plus rho h rho minus h rho. Okay? And finally, we can combine all these terms to the commutator of the Hamiltonian H with the operator C. So this is nothing but the commutator of H with C, given by this difference. And okay, C. Again, we have the first order linear equation for the operator C, subject to the zero initial condition. So the initial state rho is supposed to be pure state, so it's satisfying the idempotency condition. And again, by the unique existence theorem for the system of differential equation, we can conclude that the only solution to this equation with zero boundary condition is zero solution. So C of t is equal to 0 for all times, so the state rho is pure for all times. For all times. Do you agree? No objections? Okay. But on the other hand, thanks to the von Neumann theorem, we know that each pure state is actually described by a ket vector. So it is given by the projector. So at each time moment t, each pure state is just the projector onto the state, some state psi with node 1. So psi. So let us substitute this expression for the statistical operator into the von Neumann equation and see what this equation gives us in terms of this vector psi. In terms of this vector psi. Now, so we substitute this projector into rho, and First we compute the time derivative on the right by applying the standard Leibniz rule. We get psi prime of t, psi of t, plus psi of t, psi prime of t, on the left. And on the right we get 1 over IH bar H psi ket psi bar minus psi ket psi bar times H. This is for Neumann equation for the projector. So by definition, psi prime just the time derivative of the ket vector psi. This is my definition, shorthand notation. And to save space, it is convenient also to introduce the following auxiliary ket vector phi of t. Phi of t is given by the difference psi prime of t minus 1 over IH bar H on psi of t. This is again my definition. And in terms of this auxiliary vector phi, the original for Neumann equation for the projector takes very, very compact form. So I just move on all the terms from the right hand side to the left hand side and then combine them to get the vector phi. Then in terms of this vector phi, my equation over there takes this form. Phi of t times psi of t plus psi of t times phi of t. And now look at this equation. What does it mean? Actually, this equation tells us that the vector phi and psi are proportional to each other. They are collinear. And to prove this, we can just multiply this equation times this equation with vector psi. So take scalar product with vector psi. Since the norm of vector psi is equal to 1, it's supposed to be 1, this the first term gives us just phi of t is equal to minus, I move on this term to the right, and let me denote this function by alpha. Denote this by alpha. So I get minus psi of t times alpha of t. So indeed, vectors phi and psi are proportional to each other, must be proportional to each other whenever this projector built of psi satisfies the von Neumann equation. And now substituting this phi back to to the equation, we can bring this equation to the following form: alpha t plus alpha star t times psi of t psi of t. So we just replace phi with psi times alpha, right? We get this equation is equal to 0. What does it mean? Certainly the projector is not zero operator, it's not zero, it is non-zero operator. Hence, for this equation holds true, then the first vector should vanish. And meaning that the function alpha is purely imaginary, that alpha of t is equal to I beta of t, where beta of t takes on real values, Okay, so let us substitute this alpha to the here, and the definition of the vector phi up here to the left hand side of our equation. So as a result we get d by dt psi of t, d by dt psi of t, minus 1 or I h bar h c of t, that is vector phi, is proportional to vector psi with proportionality coefficients beta I beta t psi of t. So we get a differential equation in terms of our vector psi, ket vector psi. This equation can be further simplified. We can get rid actually of this function beta, and note that the projector psi of t times psi bar of t do not specify this ket vector psi completely, because we can always pass from psi of t to other psi tilde of t, which differs from the original psi by a phase factor. So let me replace in this equation vector psi with by vector psi tilde for the phase factor gamma of t given by the antiderivative of the function beta, that is gamma prime is equal to beta of t. Then substituting this psi tilde in our equation, we find that when this derivative hits this exponent gamma of t, it gives us some additional terms given by I beta psi, which cancel the same term on the right. So in terms of this new function psi of t, our initial equation takes the form d by c of psi of t is equal to r h of t times I h bar times h bar. And this is a celebrated Schrodinger equation for the state vector psi tilde. Actually I can remove this tilde. Doesn't matter. So this is the Schrodinger equation for the state vector. This Schrodinger equation expresses, provides a mathematical formulation of the causality principle in quantum mechanics as a first-order differential equation. And needless to say that this is a central equation of the quantum theory and perhaps the whole of physics. And in particular, in each particular representation, we can replace the state vector. We can describe the state vector by some wave function. For example, in their in X representation, for example, in X representation, instead of ket vector, we get some wave function of x and t. X and t, so that our Schrodinger equation assume the form I h bar d by dt xt is equal to h psi x t, psi xt. And this equation should be added by the initial condition, that is wave function at psi naught of x corresponding to the initial time moment t naught. So in the Schrodinger, actually this is a form in which this equation was proposed by Eigen Schrodinger in 1926. He worked in the coordinate representation, so he wrote his equation for the wave function rather than ket vector. This ket notation appeared later. It was invented by Dirac. Okay, since the Schrodinger equation is a first order in time derivative, specifying the initial state, initial wave function psi naught at some time moment t naught, we fully determine the whole evolution of the system. And this is quite similar to what happens in classical mechanics, where we specify pure states by the position and momentum vectors. And given position and momentum, then using the Hamiltonian equation, we can reconstruct the whole trajectory for our system, that is, the whole evolution of the classical system. In quantum mechanics, the initial state, psi naught, pure state, is specified by some complete set of observables. And from this perspective, the dynamical problems we solve in classical and quantum mechanics, they are quite similar to each other. And they are formulated as follows. Given an initial state, pure state, defined by some complete set of observables, either by x, p, or some value function psi. Find all the subsequent states the system will get through in the course of its evolution. And in classical mechanics, we use Newton's or Hamilton or Lagrangian equations for this, but in quantum mechanics, we use Schrodinger equation for this purpose. Okay. Any questions? Please. Maybe some other people have questions. Okay, if no questions, let us finish our lecture.